Let's take a look at resonance, damping, and forcing. So if you have some kind of realistic physical system and you displace it from its equilibrium point and release it, very often that system will oscillate at some frequency, some kind of inherent frequency. And this is called the system's natural frequency. So an example of this would be if you have a rubber band and you put it between your fingers and then you displace the rubber band, you pluck the rubber band, then the rubber band will oscillate at some set frequency. And that's its natural frequency. Now you can change its natural frequency by changing its physical characteristics. You could move your fingers further apart, and then it'll have a different natural frequency. Or you could exchange the rubber band for one with thicker rubber, and that would have a different natural frequency. Now, another example of that would be a tuning fork. A tuning fork, if you displace it from its equilibrium by, say, hitting it with a mallet, then it will oscillate back and forth at some natural frequency. Another example is car shocks. So if you have the back wheels of a car and there's those big springs that support the back wheels, the back axle of the car, that has some kind of natural frequency. Also, it turns out that the beams in a building very often have some kind of natural frequency, and that turns out to be very important if you're, say, an architect designing a building. Another example would be the span of a bridge. And you're an architect designing a bridge, that span of a bridge could have some kind of natural frequency that it'll oscillate at. Now, in most systems, once it starts oscillating at that natural frequency, there is some way for the system to lose that energy contained in the oscillation. Usually, the way that it can lose energy is through friction or air resistance, something of that sort. And this loss of energy of the system is called damping. So I'm going to draw a system. Imagine we have some kind of system that oscillates if you displace it from equilibrium. And I'm going to draw the undamped system. So this is a displacement versus time graph. Let's say that there is no damping force, then the system will just continuously oscillate forever like that. That's an undamped situation. And now let's compare it to a system where we have some small damping force. So light or underdamped system. And then it would look something like this. Notice that the period is slightly larger, and the amplitude of the system is decreasing. It's decaying over time. And in fact, it turns out that that's an exponential decay. So if I draw a curve that is just touching the tops, the maxima of these oscillations, that is an exponential function for the underdamped system or lightly damped system. Now imagine we have another system, and it has a very large damping force. So for a very large damping force, that's called a heavy damping system or overdamped system, then the damping force is so great that it never even gets a chance to oscillate. The damping force is so great that it approaches its equilibrium, but it never reaches it. An example of a system like this might be really strong car shocks, where you can imagine you push down on the back of the car and then you release it, and the car goes back up. It doesn't bounce, it just goes back up towards its equilibrium and never actually reaches it. Now, there's a point between this underdamped system and overdamped system, and that's called a critically damped system. A critically damped system is one where you displace it from equilibrium, and when you release it, it heads back towards equilibrium, but it takes an infinite amount of time to reach that equilibrium. Another way to think about these situations is imagine you have a mass spring system, and the mass spring system is in vacuum. Well, if it's in vacuum, then there's very little way for it to lose energy. Now, there might be some way through friction, say, but there's no air resistance. And so if it's in a vacuum, then it very well could be similar to an undamped situation. And now we imagine we take that mass spring system and we put it in just air, like in a normal room. That would be a lightly damped or underdamped situation where it would slowly lose energy over time and its oscillation amplitude would decrease and decrease and decrease. And now imagine we do that. We take the mass spring system and we place it in very thick oil. And we displace it from equilibrium and we release it. Well, that's going to have a very strong damping force, very strong fluid resistance force, and that would be an example of a heavily damped or over damped system. And in fact, I will show you an example of these two. If you look at the YouTube comments, I'll connect to two videos that I made a very long time ago about uh, an underdamped situation and an overdamped situation, like I just described. Now, consider the opposite of damping. So imagine you don't have a force that's going to remove energy from the system, but instead you have a force that's going to push or force the system at regular intervals and add energy to the system. This would be called a driving force. And if the driving force is being applied at regular intervals, then it has some kind of driving frequency. Now, what's interesting is if that driving frequency of your driving force is close to the natural frequency, turns out the amplitude of the oscillation will increase rapidly, and the energy contained in that oscillation will continually increase. This is called resonance. Now, resonance is something that's achieved not immediately, it's achieved after waiting for the driving force to add energy. But when it's achieved, it's usually very noticeable. Now, what I'm going to do is I'm going to draw a diagram, draw a graph, and on the vertical axis here, I'm going to have the amplitude of the system's oscillation. And on the horizontal axis, I'm going to have the driving frequency of our driving force. And right here, this vertical line that I've got drawn right there, that corresponds to the natural frequency of the system. So if we have a system and it's damped and we have a driving frequency, then we'd probably get something like this. Notice that the amplitude of the system's oscillation is max right around when the driving frequency is approximately the natural frequency. Now, if there's no damping, if there's no way for the energy to be removed for the system, then we can get a curve that's like this. Notice there's a huge spike right there when the driving frequency is approximately the natural frequency. And the reason why it's a spike is because if there's no damping force, there's no way for the system to remove any energy. And that driving force is just going to add energy and add energy and add energy until the amplitude of the oscillation is enormous. Now, one example of resonance that stands out to me from my own experience is when I was in college, there was a pedestrian bridge. This bridge was between my dorm and the physics department, so I walked on it a lot. If you were on this pedestrian bridge and you jumped at just the right frequency, right, you could find the resonance of that bridge. So this bridge had a natural frequency, and if I jumped at that frequency, the act of my feet pushing on the bridge was a driving force. And if that driving force had a driving frequency approximately equal to the natural frequency of the bridge, then the amplitude of oscillation of the bridge would increase. And it would increase to the point that you could feel the bridge moving up and down. Now, I'd always heard through the college that they insisted that there were damping forces in place and that jumping on the bridge at the natural frequency of the bridge would not cause it to catastrophically break because those damping forces would remove energy. But it was a little bit unsettling to be able to jump on a bridge at just the right frequency to cause an amplitude of oscillation like that. Now, there are a lot of other famous examples of resonance. One example is the Millennium Footbridge in London, and I'll try to link down below to that. Another example of resonance that is positive is a microwave oven. So it turns out that water molecules have a certain resonance frequency. And if you force them by sending in electromagnetic waves, and these electromagnetic waves cause the water molecules to oscillate at their natural frequency, you can cause the water molecules to have a large amplitude of oscillation. And what this amounts to is that the water molecules oscillate, which means they heat up. And that's how you heat up food in a microwave oven. You cause the water molecules to oscillate by driving them at their natural frequency.